So we talked about solving trig equations, and I told you there's basically 4 different types. Right? There's trig equations in linear form, right, which were the ones that we started and I'll talk about again. There's trig equations with multiple angles, which are bears, and students usually get wrong. But the multiple angle means that you have an extra number in front of the x. Okay? Those are different than linear trig equations, which just have a 1x. Then there's quadratic trig equations, which have some sort of trig function squared. Trig function squared is telling you quadratic. And then there's other types of trig equations, which are trig equations like number 67, where you have 2 different trig functions, for example, and you have to use identities to simplify them. And I'm just going to jump right in. Back to the examples.
We went over the first 3 couple of Wednesdays ago, didn't we?
Oh, say that again. Yes, we went over the first 2. I think we left off on tangent. Tangent k equals 1. Now remember, I told you to pay special attention to the instructions. So for example, these instructions say find all solutions to each equation. When it says find all solutions, this is when you use, you get some answer, but then you're going to add 2 pi n usually, right? Or 2 pi k or whatever extra, I don't know, I'll use n, I don't know, maybe we'll use k. But this extra n here tells you that you can add any number of revolutions, right? This 2 pi n tells you you can add any number of revolutions to your original answer, and you still get another answer to the equation. So on part C, just scroll down, I want you to solve the equation tan theta equals 1. So I want you to find all the thetas, all the angles that make tangent equal 1. Now, because the trig function is already isolated, you don't have any algebra to do. You don't have to move anything around. Like, for example, if it were 2 tan theta equals 2, what would you have to do first? Divide both sides by 2, right? So that would isolate your trig function. So you need to keep this in mind. Right, I started with this example because it's where we left off, but we have another example where you have to sometimes move around the extra numbers using algebra to get your trig function isolated. Once you have your trig function isolated, how do you figure out what theta is? Okay, so this is where you have to I turn to the unit circle. But if you have a table memorized or however you know your trig values, I'll just use the unit circle. Right, I turn to the unit circle and I say, where are all the angles that make tangent equal to 1? Maybe you don't know your tangent values, which would be a shame. If you don't have your tangent values memorized, at least you should have your x and y values. Right? 1, 2, 3, 1, 2, 3, over 2, over 2, over 2, over 2, over 2. So where's tangent going to be equal to 1 on this chart? Pi over 4, right? Because x and y are the same, so when you divide y over x, you get 1. Another helpful thing to have memorized are just straight up tangent values. Right? Tangent goes root 3 over 3, 1, root 3. And those are pretty much the only, and then you have 0 down here and undefined up here. So those are all the tangent values we know. But focusing on this chart, I know that when theta is pi over 4, tangent is 1. So one solution to this equation is what? Theta equals pi over 4. That's one possible solution, right? Just by focusing on this angle. Is that the only possible solution? No. Where is another angle where tangent's equal to 1? pick this guy, that's no good because tangent will be -1. But down here, you have -√2/2, -√2/2. When you divide those, tangent will be +1 again. So this angle is 5π/4. So another solution, another specific solution to this equation will be theta equals 5π/4. And then if you're just sort of following a procedure, right, just looking back at your notes or looking back at other problem examples and following a procedure, you might say, oh, I have to find all solutions, so let me write plus 2πn in circle. Plus 2πn in circle. Is this incorrect? Is this all the solutions to this equation? Either I land here or I land here. These are all the possible ways I can land at any π/4. I can terminate at π/4. Right? π/4 plus 2πn are all the possible ways I can terminate at π/4. And these are all the possible angles that terminate at 5π/4. Is this the simplest way to write the answer?
No.
No.
There's a way to get rid of it. Don't you have to get rid of the 2?
Well, in the case of tangent and cotangent, your period is not 2π anymore. Right? The reason we've used 2πn usually is because sine and cosine have a period of 2π. So they repeat every 2π. But in the case of tangent, it actually repeats every π. Right? The period of tangent is π. So for tangent, you can combine these and say this is the same thing as π/4 plus n π. So start at π/4, right here, that's a possible answer, and then go half revolution. Right, 1 π, that'll give you another answer. 2 π, that'll give you another answer. 3 π, that'll give you another answer. So either go π/4 and 5π/4 and then do full revolutions, or do π/4 and do half revolutions. In fact, you could replace this. Is there another way to write this? What else might be acceptable here?
5π/4 plus n.
Yeah. Why is this the same as this? Yeah, you end up in all the same spots. You're going to start at 5π/4, but then you're going to go half revolutions backward and forward. So if you go a half revolution back, you get π/4 again. If you go back again, you'll get another solution, right? But you're still singling out these two rays. I will take either these two, or this one, or this. As long as you list all the solutions, I'm fine. I'm not going to insist on a particular comment. But you will see certainly in the book, it'll start writing this kind of solution for tangent. Right, where it just has an n pi instead of a 2 pi. Any questions? Super bueno? Loudly bueno?
Yeah. So for the π/4 plus 2πn,
Yeah.
if we were to write just those two answers, but with just n pi, would that be wrong?
π/4 plus n pi?
Yeah.
And then 5π/4 plus n pi?
Yeah.
Both of these?
Just, I mean, I know it's the same as that, but never mind.
Right, so it's just redundant.
Okay.
It would be like, you know, x equals 2/2 or x equals 1. You know what I mean? It's like, what would you say? So by this or here, I kind of meant, well, you can do this one, but if you're feeling fancy, you can do this one. Either one. Let me move on to a different type. So if you have a linear trig equation, meaning you can isolate the trig function. Then you just isolate it and go to your unit circle. Remember to add the 2 pi n for all the extra revolutions you can possibly have. Okay. Okay. All right. What's different right now? What's different about part A here? Why is this a different type of equation? It's got a number in front of the x. It's got a number being multiplied by the x. So this is what I call an equation, or a multiple angle equation. Right? Because 2 theta means you have a multiple in front of your angle. 2 times the angle. So let's see here. More than that, the instructions don't say find all solutions, but instead they say solve each equation on the interval 0 to 2 pi. That's a little different than the last example, too. So the first, right, the idea here is you want to sort of translate, first you want to answer the question, well, what happens if this weren't 2x? Okay, what happens if I didn't have a multiple angle? What happens if I were just solving cos theta equals root 2 over 2? Right, what would I get for that? How would I do that? You turn to your unit circle and look for where the x value, because it's cosine, look for where the x value is root 2 over 2. So either here, or what other quadrant?
4.
4, right down here. So on the interval 0 to 2 pi, this angle is,
It's bad to the
this angle is pi over 4. And what's this other one?
7 pi.
7 pi over 4. Now, I'm going to show you a wrong answer, an incomplete answer at best, and then we'll fix it up, because I want you to understand why this is incomplete. So one way to proceed from here would be to say, okay, well, I know what angles give me root 2 over 2. So instead of having theta, though, I actually have 2x. So instead of saying theta has to equal pi over 4, I could say 2x has to equal pi over 4. As long as I make this whole thing in here pi over 4, I will get root 2 over 2 out. So one way to proceed from here is to say, okay, this 2x has to equal pi over 4, and then solve for x. Or the 2x could equal what? What's my other option? 7 pi over 4. Right, in either one of these cases, I can solve for x and get my solutions. So for example, what would x be here?
Pi over 8.
Pi over 8. Why?
Because you divide it and then
Divide by 2.
flip and multiply.
Now, just to save myself a little room, instead of just dividing by 2, I'm going to start from the beginning, multiplying by 1/2. So that will give me x equals pi over 8, because that gets rid of my 2 here. And then back here, if I do the same thing, times 1/2 times 1/2, x is equal to 7 pi over 8. Said solve on 0 to 2 pi. Boom, done. Remember, this is incorrect. Partially incorrect. Why is this incorrect? Because who?
Supposed to just be on from 0. Zero is supposed to be from 0 to 2 pi.
Okay. So I got my two solutions between 0 and 2 pi.
Yeah.
You didn't put in the
I didn't do it. This was
Oh.
7 pi over 4. So when theta is pi over 4, then 2x has to equal pi over 4. Here's your answer. If theta is 7 pi over 4, 2x has to equal 7 pi over 4. Here's your answer.
But you could put plus 2 pi and
Yeah, so the problem with this is it's not getting all the solutions on 0 to 2 pi. It's only getting half the solutions on 0 to 2 pi. So what I mean is, for example, what happens if I were to plug in, try 9 pi over 8. What happens if you put 9 pi over 8 in for x? Cosine of 2 times 9 pi over 8. Do you see that this 2 and this 8 are going to cancel? And leave you with a 4 on the bottom? What's cosine of 9 pi over 4? 9 pi over 4 lands here. Cosine of 9 pi over 4 is root 2 over 2. So 9 pi over 8 should be another solution. Right? It's less than 2 pi. How do I know this is less than 2 pi? Yeah, if you change it into a mixed number, 8 goes into 9, 1 and 1/8. Right? So this is less than 2 pi. But it's not accounted for in this strategy. Okay. So one way to make up for this, for these extra solutions that you're missing, is when you initially solve for theta, find all solutions. So add in that 2 pi n. Right? So instead of writing theta equals pi over 4, write theta equals pi over 4 plus 2 pi n. And then when you solve for x, you put 2x equals pi over 4 plus 2 pi n. What's that going to change? Well, I still want to isolate x, so I still multiply everything by 1/2, including the 2 pi n. So all possible solutions to this equation coming from this angle are pi over 8 plus what happens here when you have 2 pi times 1/2. You get rid of the 2. Now this is all solutions. 1/2 of all solutions. And I do the same thing over here. To make sure I get all possible solutions on 0 to 2 pi, I add in my extra revolutions. I add it in down here. But then when I multiply by 1/2, I have to multiply this guy by 1/2. So all possible solutions on this end is 7 pi over 8 plus 2's cancel, pi n. But wait, you say, Josh. This is confusing. Okay, fine. Also, that's all solutions, and I only asked you to solve on 0 to 2 pi. So how can I use this to get only the solutions between 0 and 2 pi? The point of getting all solutions is that it gives you a formula you can use to find the specific solutions between 0 and 2 pi. So you can now go to this formula and plug in n equals 0, n equals 1, n equals 2, and you will end up getting all the solutions between 0 to 2 pi. In fact, you'll end up getting solutions that are too big, and that's how you know that you should stop plugging in n's. So to get just the solutions from 0 to 2 pi, you start plugging in n equals 0. n equals 1, n equals 2, and see what happens. When n equals 0, what does this formula tell me?
It's pi over 8.
Pi over 8. That's what we thought it should be, right? That was one answer we thought we should have. Right? Because if n is 0, this is gone. Cool. What about this formula when n equals 0?
7 pi over 9. Or 8.
7 pi over 8. Right? When n equals 0, this whole extra n pi goes away. So here's two of my solutions, but that's not all of them. Keep going. When n equals 1, what happens here? You have to do pi over 8 plus pi.
9 pi over 8.
Yeah, because you put in an 8 and an 8. Pi over 8 plus 8 pi over 8 is 9 pi over 8. There's the solution we were missing the first time, one of them. And then when you put n equals 1 in here, 7 pi over 8 plus pi, right, when n equals 1,
15 pi over 8.
change it to common denominator. 7 pi over 8 plus 8 pi over 8 is 15 pi over 8. Do I need to worry about n equals 2? Why not?
It's 15 pi over 8 is almost 2 pi.
First of all, the 15 pi over 8 is pretty close to 2 pi, right? Because 8, if this gets to 16, that's 2 pi. So this one's right on the edge. The other way is, if you put in 2 here, pi over 8 plus 2 pi, that's too big, right? Pi over 8 plus another 2 pi, that's going to be too big. 7 pi over 8 plus a whole other 2 pi, that's going to be too big. Sort of, so these are your solutions to this equation on this interval. And the rule of thumb is, whatever your multiple is here, you're going to have that many times extra solutions. So what I mean is, originally cos theta had 2 equals root 2 over 2 had 2 solutions. But because we did cos 2x, we have 4 solutions. We doubled our solutions. If I made this cos 5x equals root 2 over 2, how many solutions do you think you'll have? 10. Right? You do 5 times the original number of solutions. Now, there's a couple other ways to look at this, okay, a couple other ways to do it. This is a procedure that will always work, even though it's a little tedious. So this is what I'll do. But if you're ingenious and you discover another method that always works for you, that's fine. Kind of the strategy here, right? What I will always do when I have a multiple angle is I'll first find all solutions to this related equation. So step 1 was finding all solutions to the non-multiple angle equation. Non-multiple. Right, so pretend it was just a theta and find all the solutions. Then replace the theta with x's, right? Replace the non-multiple angle with the multiple angle. And solve for x. Once you've solved for x, you'll have a formula for x, and then you can plug in different n values until you get over 2 pi. Start with 0, then go to 1, then go to 2, and keep going until you get to answers that are too big. so that we can kind of streamline this so you can see how it goes. But questions about the theory here? Questions about what I did? Kind of makes sense? Try another one. Now also you have to be careful. It does say solve each equation on the interval 0 to 2 pi. That's why I'm going in and plugging n values. That way I can get angles that are between 0 and 2 pi. What if it would have said find all solutions up at top? Stop right here. Right? Because this is all solutions. All solutions. So because it says solve on 0 to 2 pi, I have to go in and plug in extra n. If it just said find all solutions, I can stop at number 3. Step 3. Well, let's try B. Tan 3x minus root 3 equals 0. How am I gonna handle this equation?
Can you divide everything by 3?
Yeah. So the first thing I would do is isolate the tangent. Right? Meaning I can move over this root 3 and I can divide by this 3 here. So isolate the trig function first to make it look more like part A, where you just have a trig function equal to none. So isolate first here. Add root 3. 3 tan 3x equals root 3. Now be careful, because there is a big difference between this 3 and this 3. This 3 is outside, connected by multiplication. This can be divided. This 3 can't be moved. Right? He's permanently there. At least for now. Permanently for now. So I'll divide by this outside 3, and I'll get tan 3x equals root 3 over 3.
So why can't you divide by the 3 inside the tangent?
Because it's not equal. It would be like if you had 5x plus 1 squared equals 2, and you decided to divide by the 5. Like there are other things in the way before you can get to that. So once we get rid of this tangent, then you'll be able to divide by the 3. But right now the tangent's trapping it. It's like I can't divide by this 5 until I get rid of this square. And then move the 1. So you have to take care of this tangent first. And the way to take care of the tangent is to solve the kind of, right, is to ignore the multiple angle for a second and just answer the question, where is tangent of theta equal to root 3 over 3? So do you remember where tangent's equal to root 3 over 3?
Pi over 6.
Yeah, those tangent values go like this. Root 3 over 3, 1, root 3. So tangent is going to be equal to root 3 over 3 at pi over 6. Do I need the other answer over here? Right, there's another place where tangent's equal to root 3 over 3 down here. Right, this one doesn't work because it's negative. And this one doesn't work because it's negative. Tangent's negative in 2 4. But this guy's okay. Right, 7 pi over 6 is another answer. Do I need both of those? Why or why not?
Not really, because you're just going to add pi in.
Yeah, not really. I mean, you could use both of them, right? At this point, you can either say theta equals pi over 6 plus 2 pi n, right, to find all solutions, or theta equals 7 pi over 6 plus 2 pi n. You can use both of these equations, or you can combine them into one and say theta equals what?
Pi over 6 plus pi n.
pi over 6 plus 1 pi n. Right, because tangent repeats every pi. So you can just take one of the answers and add pi n. So this is what I would use for this equation, tan theta equals root 3 over. And nobody cares about theta. Right? Theta was nowhere in my original question. In my original question, there were x's. So the answer to this equation is theta equals pi over 6 plus pi n. So then how do I translate that back to my x's? 3x equals, right. If theta is equal to this, well, theta and 3x are the same thing. Right? That's what I'm saying right here. So you can think of this as 3x equals pi over 6 plus pi. And that's what you have to solve. That'll get you your x answers. How do you get rid of that 3 now that the tangent's gone? Now that the tangent's gone, you can divide it. Or, if you're Josh, you'll multiply by 1/3. Then it'll fit. Takes up less space. Right, so multiplying by 1/3 is the same as dividing by 3. You'll get rid of your 3. You got to do it to every term. So here, the 1/3 and the 3 on bottom, 3 on top, they cancel. Pi over 6 times 1/3, what's that?
Pi over 18.
Pi over 18, so equals 1. Pi n times 1/3?
Pi n over 3.
Pi n over 3. If I had been nice to you and said find all solutions, you'd circle this and be done. But I was not nice. And I said solve on the interval 0 to 2 pi. So you've listed all possible solutions, but I only want the ones that go between 0 and 2 pi. So what do I do?
Plug in 0 for n.
Plug in n. Plug in n values. Plug in n equals 0, equals 1, 2, 3, 1. Plug in n values until you get answers that are bigger than 2 pi. One thing that might make your life a little easier as you plug in all these n values is the common denominator. Right? Because I'm going to have to get a common denominator every time I plug in n, so I might as well just get a common denominator right here. So to save myself a little bit of time, I can change these both to 18s by multiplying 6 over 6. So when I get a common denominator, I know that x has to equal pi plus 6 pi n over 18. Here's all solutions. Right, because this becomes 6 pi n, this becomes 18. So pi plus 6 pi n. And then you plug in. When n equals 0, what do you get?
Pi over 18.
Pi over 18. There's the first solution, right? If n equals 0, this guy's useless. Pi over 18. My black is dying. If n equals 1, pi plus 6 pi times 1 is 7 pi over 18. So there's your x value. If n equals 2, pi plus 6 pi times 2, pi plus 12 pi, and you just keep going. pi plus 6 times 3 is 18, so this will be 19 pi over 18. Whoa, 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 whoa. Is 19 pi over 18 too big? Should I stop here? No. You might think so because 19 is bigger than 18, but I actually don't care about that. But I want to go all the way up to 2 pi. So I won't stop until I get a mixed number that's bigger than 2. Keep going. N equals 4. Will be another 6 pi added to that. 5. Another 6 pi added to that. What about n equals 6? Well, pi plus 6 times 6 is 36. Pi plus 36 pi is 37 pi. 37 pi over 18, how do you feel about that? Too big, right? 37 is more than 36. This mixed number is going to be bigger than 2. So here's your 6 answers between 0 and 2. This is the tedious part. Okay, we're plugging it in, it gets tedious. This part over here is not super difficult, right? You change your equation to a theta, right? We saw tan theta equals root 3 over 3, which was pretty easy. Then we replace the theta with 3x, and we get all solutions. Plugging in the ends. That's the way you can get solutions between 0 and 2. Questions?
Is that how you write it for the answer? Just kind of
You can, yeah.
list all 6?
Yeah, that's fine, as long as you circle them all. Another way you could write it if you wanted to, you could put it in a solution set and just list them out. Pi over 18, 7 pi over 18, 13 pi over 18. Right, just keep listing them out.
Well, like the quiz, we just circle.
Either one's fine. Does it surprise you that there's 6 solutions?
Nope.
No.
Because there's 2 and then you have to multiply.
Originally there was 2, but it was a 3x here, so we know there's going to be 3 times 2, which is 6 solutions. All right, let me show you what got it. So you kind of have to remember, so I'm moving on to the next type, which is quadratic trig equations. So if you look in these examples now, they all have square. Right? Cosine squared, sine squared, tan squared. So to solve quadratic trig equations, you kind of have to remember how to solve regular quadratic equations. So what are your methods for solving quadratic equations? Do you remember? Factoring. Right, that's the method I would use most of the time if I could because it's fast. Right, so for quadratic equations, you can factor. You can use the formula. Quadratic formula. And sometimes, if they're simple enough, you can just square root both sides. You can only do that if it's a simple quadratic equation. But I have an example like that. There was also completing the square. If you remember that, you can use that. But the quadratic formula and completing the square do the same thing. Most of the time, you'll be able to factor on these questions, but not always. So quickly, let's do cos, so let's do part A here, the equation, solve on 0 to 2 pi. 2 cos squared x plus 3 cos x plus 1 equals 0. All right, as soon as you see this cos squared, you know you're dealing with a different animal than we've been dealing with. So what I would like you to imagine in your head, I would think of this cosine here as an entire variable. Think of this guy like some u variable. I don't want to use x because x is right here. It's like some u. Then what would this cos squared be equal to? U squared. So really the equation at its heart, if you cut out the trig portion, the equation is just 2u squared plus 3u plus 1 equals 0. And this you can solve. How do you solve this? Factor. You can factor it. So you break this down. You say, okay, what two things multiply out to 2u squared? Well, 2u and u. Right? 2u times u is 2u squared. And then you have to be careful. You want the other terms to multiply out to 1. And then how do you check that this is correct? Foil it, or in your head foil it at least. Right? You say, all right, well, this is giving me 1u, and this is giving me 2u. So when I add those up, 1u plus 2u is 3u. You have to check and make sure the middle adds up. So these two multiply out to the 2u squared. These two multiply out to the 1. But then you check your inner and your outer and make sure it adds up to the middle. So once you factor this, however you factor it, if you factor it differently, that's fine. But once you get from here to here, what does this tell you? How does this help? Set each one to 0. Right? You have a product. You have a product equals 0. So you can say, all right, well, 2u plus 1 equals 0, or u plus 1 equals 0, right? That's how we solve quadratics. And then these are not quadratic anymore. These are linear. U is equal to -1. Or if you subtract 1, 2u is equal to -1. U is equal to -1. Circle and call it a day? All done? No! Nobody cares about you. We started with x's, right? So we have to get back to x's. So even though I made up this equation and solved it, at the end of the day I need to have x's in my answer since my equation had x's. So instead of stopping here, I'm going to substitute back in. U equals -1/2 is the same as what should I replace u with? Cos x. U is cos x. So I have to solve cos x equals -1/2, or cos x equals -1. So these are cos x's. And then for each one of these, I can go to my unit circle. Cosine's -1/2. Here and here. What two angles are those?
2 pi over 3 and 4 pi over 3.
Yeah, 2 pi over 3, 4 pi over 3. So from this equation, I get the two solutions. X equals 2 pi over 3, 4 pi over 3. Do I need plus 2n pi? Or plus 2 pi n? When do you need plus 2 pi n? There's 2 times.
The angles multiplied.
When you have a multiple angle, you're always going to find all solutions first. I don't have a multiple angle here. I don't have a number multiplying my angle. So I don't care about all solutions right now. And the other time is if the instructions literally say find all solutions. But the instructions don't say find all solutions, they say solve in 0 to 2 pi. And I don't have a multiple angle, I don't have a number being multiplied by my angle. So I can just list out these two to be done. Then I move on to this. Where is cosine -1? Well, let's see, -1, I think that's over here for my x value. So cosine is -1, and the angle is pi. So these are my three solutions. 2 pi over 3, 4 pi over 3, and pi. If you wanted to be super fancy, you could write 2 pi over 3, pi, 4 pi. Those are your solutions. But you do need all three of them. So either you put it in a set or you circle all three. You need to get to all three of those solutions.